Hi everyone. Let's finish fixed point so we can move on to the floating point. So yeah, last session we talked about how we can convert things decimal to fixed point and vice versa, and we also did arithmetic using fixed point. Now the last operation that we will look at is division. Division, I would say very briefly that try to avoid it, especially if you're dividing by an integer. As you know, like before, it's better to multiply it by a number and then shift it, right? Remember from the binary arithmetic? So in general, it's just better that if you could, when you're dividing by an integer, try to multiply by something, some equivalent number, basically. Okay? So fixed point over integer, it's easy. The only thing you have to notice is that you might lose fractional points. For example, let's divide 6.75 and cube 4.2 by 2. So the result is going to be 3.375. And now you can see that in order to store 3.375, I would actually need 3 fractional bits. But since the format is staying the same, then the last bit, the LSB, is going to be dropped. This one. So we lose some accuracy, right? Truncation error that we talked about, accuracy error that we talked about. So just remember that it's a straightforward, but you might lose some fractional bits. Now, case 2 and case 3 is just like, how you would divide anything that is multiplied by an exponent. For example, if you're dividing 1.4 multiplied by 10 to the power of 10 over 2.3 10 to the power of 2, let's say. The only thing you have to notice is that here, this is not a good example. If you're dividing, let's say 0, 0, 0, 2, and 3 over 0, 0, 1, 4, then what you want to do is first write this in the form of 2.3 10 to the power of, let's say, you want to make the formats the same. Let me just explain it that way. It's just so hard to, do this in decimal because we know how it is. Okay, so you want to make the formats the same. Then case 3, if you have different formats and you're dividing, you're going to get wrong results. So that's what you have to make sure that, like, if you're bringing numbers from different operations with different formats, first, convert them one to another and assign them to obviously a bigger size, and then do the operation, do the division, and then move on, with the rest of it. For example, when we do same format to same format, you can see like 1.5 and 0.25. If we consider both of them to be in UQ 1.2, then it's as if you are dividing 0B 1.10, that's 1.5, and this is going to be 1.25, or sorry, 0.25. And since the formats are the same, you're just getting rid of the point, and this is going to be 6. But this 6 now has no fractional point, right? And last thing you want to do is that to convert this to UQ 1.2. So you have to shift it and consider it as 6.00, or show it this way. In binary, 6 would be let's say 6 is 1, 1, 0, right? And you're going to left shift this. 1, 1, 0, 0, 0. Left shift, yes. You need to have a space to store it, obviously. Otherwise it would be 0. Does it make sense? Please.
So this really be like UQ3, right?
Yes. Otherwise, yes, it would. It wouldn't fit. What else? Yeah, and as you can see, if we, try to divide UQ 1.1 to 1.2 without considering that the exponents the fractions are different, then you're going to get the wrong result of 3. Well, I don't know who would do that because obviously they don't match, right? So general advice, replace division with multiplication. If you have to divide two, fixed points, make the formats the same and then do it. And then, yes, last thing to remember is that left shifted, so you are storing the fractional bits. Because if you store it like this, then next one is assuming that your fractional bit is here and reads this as 1.5. Does it make sense? It assumes that you have 2 fractional points. You don't want that. On the last slide I have here, anything you would need for the lab or your project, if you have to deal with fixed point, I wrote it basically, the tips to remember what to do. Any questions? In here, in division, it's really the fractional bit that gives us problems. Like how much fractional bits you have, you're storing. That's the one that you have to keep track of. Because usually, like when you're dividing, the integer becomes smaller, so you're not going to have, well, not in this example, but like it's usually you have integer bits, so you can afford this. But it's the fractional bit that sometimes you lose it, and then that causes truncation error. And then sometimes you have to shift it to bring it back to the same format. Okay. Now, again, for your exam specifically, though, I wouldn't focus too much on this, but just remember it. Now, we move on to the next version. Fixed point is very fast, as you know, but it's very rigid because the exponents or the fractional bits are fixed. Once the format is fixed, it's fixed. You can't change it. And the range is quite limited to, those number of bits that you have. The resolution and the range is going to be fixed as soon as you have defined M and N, right? But with floating point, we get rid of that. With floating point is when we get real expansion on how much we can cover real numbers, how small they can be, how big they can be, okay? So floating point is really most widely used format for real numbers, but as you would see, that it requires a special hardware. So it's not that, people don't like floating point. It's expensive. You have to spend money, chip area on it to be able to afford it. But there are lots of benefits compared to fixed point. Just before we start floating point, I put a document that says floating point versus fixed point on your Quarkus page. We are not going to cover that. It's just for you to later look at it, if you're interested, to see what's, what are the difference in the applications and speed and, test cases. Now, okay, floating point was basically defined by William Cahan, I think, and he was from U of T, so take pride in that. And then what he did was he defined the standard IEEE 754, which is the standard way we would represent floating point, basically. Now, the floating point format is that we have -1 to the power of sign bit, okay? So just like before, if the sign bit is 0, okay, -1 to the 0 is going to be 1. So that's a positive number, okay? So if sign bit is 0, then -1 to sign is 1, and that's positive number. And then you can do the other one, sign bit 1, negative number. Then we have 1 plus fraction and multiplied by 2 to the power of exponent part, okay? Now, you see that fraction is a number between 0 and 1, okay? So we always, I'll show you later, that we always show this number in terms of 1 point something. That's a standard way to keep it. 1 point something multiplied by 2 to the power of something. Just like, how you would do it for, let's say, a scientific version, right? You always have the first point after the first digit, let's say. Now, the fraction is really what comes after the binary point or decimal point here if you are converting from decimal. And then you would hear some other term. And in fact, be careful because sometimes these two terms, fraction and mantissa, are used interchangeably, but they're not the same. Okay? This is called mantissa. It's a weird word, but... So be careful between the two. And once fraction is given to us, or we found fraction, the 1 plus is given, it's implied. So it's always coming with it. So the exponent is really the one that determines the magnitude, and the fraction one determines the resolution, right? For example, let me show it here. Minus 1.003, 2 to the power of 70, let's say. Okay? The resolution is coming from here, and 2 to the power of 70 is really the one that is defining the magnitude of this number, right? So it's not like before that m had, something to do with the range. It's really the exponent. Now, the first thing you have to remember is the implicit bit or the implicit 1 here that sometimes might give you, some errors. It's that we always use the normalized notation in floating point. We always say it's 1.75, 1 point, whatever it is, it's 1 point plus the fraction that is getting multiplied. And we don't store that implied 1 anywhere. So if you're defining a number as float or as the binary series as float, it's always, you'll see that we will interpret it and then add a 1 to it. So it's implied. And that way we are saving basically 1 bit for storage. So for example, here it says like 10 to the power of 746 multiplied by 2 to the power of 6. If you want to normalize this and show it, in the floating point format, what we do is first 10.746. This is in decimal. I want to mention that. So first thing you would do is to divide this by 8. That would be, I had a solve here. It would be 10. And 746 over 8. That would be 1.34325. Now you can say this 10.746 multiplied 2 to the power of 6 is 1.34325 multiplied by 2 to the power of 3. So now we are combining the exponents. 10.746 multiplied by 2 to the power of 6 is going to be 1.343252326. Why are we doing this? Because first, whatever decimal number you get, first you have to bring it in this format, okay? Then, now later you'll see that we are going to store the exponent in some part of our, bits, the fraction in another part, and then the sign in another bit, okay? And IEEE 754 is the one that, tells you where each of these would go. So first thing we do, as soon as you get a decimal number, is to convert it to this normalized format. And then you would start converting these to bits and putting them in the right place, basically. So there is some history here because before floating point, people were using it, but then nobody knew which ones are the fractional bits or not. Believe it or not, and people were doing this, based on their liking. They were assigning different bits to fraction or different number of bits to fraction bits, and then the rest of them for the exponents. And then after this standard was defined, then they could reproduce, they could, compare things. And then the beauty of it is that later you'll see that something that we couldn't do with fixed point was the special values, like infinity or, subnormal. We know we have underflow going on. If you get below a range, the smallest possible value, then you would go underflow, right? But here, this standard, you'll see that it allows you to go gradually to underflow. Before reaching there, you can still show some small values. So, this is the formula you're going to care about. It's again minus 1 to the power of sine plus multiplied by plus 1 plus fraction, and then 2 to the power of actual exponent. We say here actual exponent because we're not going to store exponent as it is. We're not going to store minus 2 or something like that, right? What we store is that we add a bias to the actual exponent. For example, here, this is the FP32 standard. I will talk about this. You have 1 bit of sine, and it's always following this order. 1 bit of sine, then the exponent's bits come in, and then the fractional bits come, okay? For FP32, we have 8 bits of exponent. The rest of it is fractional beside the sine bit. So when you have 8 bits of exponents, right? If you get it as assigned, what is the range you can cover? Let's say we have 8 bits of exponent. If we were going to show it as signed, what was the range? Anyone? A signed 8-bit integer. What is the range? Go ahead.
Minus 2 to the power 8 to 2 to the power 8
Minus.
2 to the power 8.
You have one of it as signed, right? So to the power of 7.
Oh yeah, minus 2 to the power 7.
Right? If it was signed. But what we are going to do in order to not deal with the signed version and, 2's complement and make comparison and arithmetic of floating point much easier, what we are going to do is add 1 plus 27 to this exponent and then make this 8-bit stored exponent an unsigned value that goes from 0 to 255. Please.
So how can we get sort of 0.5 if we can't get negative exponents?
What do we forget? We get what?
Like how can we get like 0.5 if we can't get negative exponents?
So we'll see. I'll show you how, okay, in an example. Okay, so again, sign determines positive and negative. Fraction shows precision. An exponent really gives us the range. And we always have this trade-off that if you're spending more bits on the fraction or exponent, you're losing something in the range and gaining in precision. But 32-bit, you'll see the standard of FP32 is what is balanced for most applications. So I already talked about, if a number has an exponent of, let's say, what we drove before, right? Let's say this is 1.325 here, 1.34325 to the power of 9, okay? Instead of storing this 9, we make a bias. This is our actual, what we call actual exponent. We add 127 to it, and then we store 136. So we normalize, then we calculate the stored component, then we put everything together. Just before we go through that, I want to say that the previous graph that you saw was for FP32, which is this what we call single precision for floating point. We had 1 sign bit, 8 exponent bits, 23. And in C, we define it as float, simply float. And it's default for many applications. You can have half precision by 16 bits. Again, you have 1 bit of sign, 5 bits for the exponent, and then 10 fractional bits. In C, we don't really define it. We don't have a type that you can use for half precision, but you can use compilers or, in NVIDIA, especially for machine learning and stuff, you can use it as, with hardware, the correct hardware, you can define it basically. Okay. Then on the other side, we have double, which is double precision, and then it's a standard for scientific computing. So if you're doing any kind of application, let's say you're processing geology or any kind of data that needs accuracy, strong accuracy, then you would use the 64-bit. Here we use 32-bit one, so it's again FP32 is the one we use. But there are some, you'll see at the end of this, that there are some other smaller formats that recently have been used for machine learning, AI acceleration, and other stuff. They go even to 4-bit, I think. Yes, 4 bits. So for our FP32, we learned that the bias is always 127, okay? To just bring it to positive. If we had 5 bits and this was our half precision, the bias would be 15. If it was double, it was 1023. So notice that here it says stored range is from 1 to 30, 1 to 254, and the rest. But the actual range that you would get is from -14 to +15, -26 to +27. And you might be asking, okay, why am I not getting, where did 0 and 31 go if I have 5 bits, right? So those are this standard, IEEE 754, it keeps the highest and the lowest for special cases, okay? So when that, if you store 000, meaning 0, basically, that would mean one special case, and then the fractional bit and the exponent would be treated differently, and then if it's all 1, again, it would be treated differently, and you'll see later. But just remember that you don't have the full range when you're defining. You can never have 0 there and then treat it like 1 point blah. And here, there are some differences between the floating point resolution, the actual number that you get, for fixed point and versus floating point. For fixed point, the resolution was always fixed, depending on the fractional bits. But in the floating point, it really depends what's your exponent value, right? What is the maximum, the magnitude that you're representing, and then the definition of that LSB would be different. So for example, here, we are showing 10, and then if you add a small number to, let's say you make the LSB go from 0 to 1, this is the added resolution. And if you were adding 1 here to the LSB of this number, you were getting a resolution of 10 to the power of -3. And since, remember, here the binary point is not fixed. It's going to move based on the exponent, right? Because you're saying whatever this 1 point fraction is, 2 to the power of 3, you're shifting it, right? You're shifting the point, basically. Or 10 to the 2 to the power of, let's say e, sorry. As you're shifting this, you're shifting the point. So the resolution, obviously, is going to be different. I know I'm going too fast here because these are just, some rules at the beginning. Now, remember that we want to, in order to find a range that you can show with floating point, remember the exponent can't be 0, so we start from 1. And then for 32, what you can get is, remember that 1 point f multiplied by 2 to the power of e that you store, I'm going to call it e stored, minus 127. So considering that this can't be 0 for normal numbers, if it's 1 and f is 0, that would give you the smallest one. This is the smallest positive number. Now the largest one is going to be, again, you can't have this, all ones for the exponent. So you would have 1 f to the power of e minus s. And if this E is, it can't be, E is stored minus 127. It can't be all 1, but what you can have is have this as 1.9 or whatever, like very close to 2, but minus that, the last 23rd bit of the fractional one. And here, we are just putting 254 here, basically, because that's the available one. And it's not going to the special case. Let's do an example, so this all would make sense, okay? We have minus 70.8053, and we want to convert it into the floating point, okay? So the sign bit, what is the sign bit? 1, perfect. So we have negative, so sign bit is 1. Then we have to normalize this, right? Bring it to the 1. Remember, this is, I'm going to write it here. Minus 1 to sine 2 to the power of E minus 127. We have to find this version. So we have to normalize this. Minus 70.8053. In order to bring it to the 1 point something, I should divide it by what? What? 64. Perfect. And then I have to remember that I have to multiply it by 64 too. Okay. So, sorry, this is plus. Once you get the sign bit, you don't have to care about this. So, again, that's a pretty thing about like floating point. You don't care about the 2's complement or anything like that. You just get the sign bit, and the rest of it is just like binary, regular binary integer, basically. 80.53 over 64. So, I really didn't think this example through because you'll see what happens. Multiplied by 64, which is 2 to the power of 6, right? Okay. Now, we have to remember that this is our actual component, 6 is our actual component, and what we are going to store is 6 plus 127. So it's 133. This is what we are storing. So immediately I'm just going to go to here because fractional one is the one we have to say. What is 133? And we are presenting this in 8-bit. So this is 0b in 133 is 127, which is so let's show it this way. 3, 4, 5, 6, 7, 8, right? This is 64. This is 128. So it's 1 here. Then it's going to be 128 plus 1. Plus 5, sorry. So that's 1, 0, 0, 0, 0, That's 133 basically, as an unsigned integer. Okay, perfect. We got the sign bit, we got the exponent bit, so I'm gonna write them here. This is sign bit, this is the exponent bits. So sign, exponent, and then we need to find the fraction. Okay? So for fraction, again, everything is unsigned. Very easy. Our fraction, we extract the 1. This is all we care about. This is going to be 0, 1, 0, 6, 3, 3, 2, 8, 1, 25. Okay? We are converting this to binary, and we have 23 bits for it. So let's remember FP 32, 1 bit for the sign, 8 bits for the exponent, and in total we have 32. So this is going to be for our fraction. This is So we are showing this, exactly this fraction number in UQ 023. Or as you know it, this can be shown as UQ 23, like this. So in order to do that, we multiply it, remember from fixed point? We multiply it by 2 to the power of 23. And then we round it to the closest integer, right? Does everybody remember this? Okay, so now that's what we are going to do. That's 891, 984, 28, 16. Closest integer to this going to be round to closest integer. That is going to be 891, 984. Correct? Now we are going to show this as an unsigned binary bits, basically. Okay, now let's see. This is in 0B. Oh, it's a really long one. Okay, 1 1 0 1 1 0 0 1 1 1 0 0 0. Gonna bring it here for the rest of it. Then so how many is it? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20, and then you add 3 zeros here. So the fractional one is going to be this one here. One one zero one one zero zero one one. So this is going to be all of our 32 bits. And by the way, you have a quiz on fixed point and floating point, and because we haven't finished it, and we'll finish floating point tomorrow, the deadline got extended to end of Sunday, basically. Go ahead.
I'm just wondering, what's the difference between just saying it's a fixed point with Q 8.23? Wouldn't it just be the same? Like, what's the point of floating point in this case?
In this case, this
Like
one.
if I said this example was a fixed point,
Mhm.
Q 8.23,
Yeah.
wouldn't it have been the same thing? Like, where does floating point come in handy?
Okay, so this is an example we are doing by hand. Intentionally, it's a number, right? That you can fit it with the fixed point with 32-bit, let's say, right? But if it was really larger, remember the range for fixed point was like minus 2 to the power of m minus m, blah, 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 right? So the maximum number you can show with fixed point is 2 to the power of, what did you say, 8.23? So that's going to be 2 to the power of 7, right? That's the maximum of the positive side. On the negative side, to the power of 7, right?
Is that not the same thing as the floating point? Because floating point,
I'll show you the range. The range here is going to be exponentially is going to go high, because every bit you add to the exponents, like 8 bits that you get, remember that the exponent can go from minus, look at it here. The exponent, the actual one, where did I put this? Oh. Yeah, here. This is the range of your exponent. So your exponent can be, your number can be 1.7, the maximum, multiplied by 2 to the power of 27.
okay.
You see? By just 8 bits, right? Or like, for example, here I said it. Here, the smallest you can cover is 1.18 multiplied by 10 to the power of minus 38. And then here, 10 to the power of 30 plus. So you see, it's not even comparable for the range. Yeah, I see this number, and that's a great point. Like for these small numbers that fit within the 32 bits of fixed point, sure. But once you have to have those numbers, no. Okay, let's do the reverse one, and then we solve more examples tomorrow. Here we are doing the reverse, which is interpreting, okay? So we have 32 bits, and we want to find what is the decimal value for this, okay? Extracting the sign. The first bit is the sign. Is this positive or negative? Positive. Sign is 0, so this must be a positive number. Then we are extracting the exponent. The next 8 bits are the exponent. So I'm going to put it here. So this is the sign 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the exponent is, the stored one is 0, 1, 1, 1, 1, 1, 1, 1. What is this? $128 minus 1, right? 127. That's 127. This is our stored one, right? So what was our actual one? E stored is equal to E actual, let's call it, plus 127, right? So our actual exponent is 0, in fact. And that's going to be 1f plus 1f so far, multiplied by 2 to the power of 0. Okay? Now the fraction. Oh, our fraction is completely 0. Okay, let's add some ones in here to make it interesting. Okay? And then we have to change this number. But then the fraction is going to be, let's call it 0, 1, 1. The rest of it is 0. And this is the point before, right? You know, this is 0.25 plus 0.125. So it's 0.375. So what did we get? Value is going to be plus 1 point fraction, which is 375, 2 to the power of 0. So that's 1,375. Good? I have to update this one. I don't know. This is 3, this is F. And now I made this 8 plus 3, which is 11, right? That's going to be B. So we solved this one, just to make it more interesting. Okay, since we are super quick about this, let's solve the other example too. Okay, so here the first bit again is 1. So our sign is going to be negative. And then we have the exponent that is 0, 1, 1, 1, 1, 1, 1, 0. Okay, and this is 0b. Going to show it. When we show 0b, that before the bits, it means it's binary. Okay, so now we are going to show it in decimal. What is this number in decimal? 126. Thank you. 126, and this is our stored exponent. Then our actual one is going to be what? Is going to be 126 minus 127. That's minus 1, right? Then we need the fraction. So we counted till here. The fraction is going to be point. Don't forget the point. 0, 0, whatever, the rest of it. And you know this already. This is 0.5. So our number is going to be minus 1.5 multiplied by 2 to the power of minus 1. No, sorry, 2. 2. And that is minus 75. Again, these are very straightforward examples. Hopefully you see some harder ones in the exam. So, thank you, everyone.